Whether you're a mechanical engineering student or addicted to engineering, a jet engine is a topic that is liked by everyone. Jet engines have transformed air travel since their widespread adoption more than half a century ago. The power delivered by these revolutionary engines has allowed humans to fly further, faster, and cheaper than ever before. But how do these engines work? In this video, we're going to discuss how jet engines work. The video is going to be amazing, so make sure you stick till the end. Modern aircraft are powered by gas turbine engines that pass air through a series of stages where it's compressed, ignited, and expelled. This process creates a high-pressure exhaust that is used to drive rotating engine parts and produce thrust. Their development and refinement over the course of the last 65 years have made commercial air travel more practical and profitable, opening the world to business and recreational travelers. Around 1800, George Cayley invented the steam engine. After that, in 1884, Sir Charles Parsons' invention did amazing work regarding the steam turbine and compressor. Have you ever heard about the Ramjet? You might have heard this word in your school while learning history. Ramjet is the simplest type of jet engine. Later, in 1910, Sir Henry discovered the jet-like plane where he used a big fan instead of a propeller. After several years, which means in 1936, Whittle invented the turbofan engine. For this invention, he also filed a patent. In 2019, Gen X is the most used engine in jet airplanes. This engine produces less thrust but works with high efficiency. There are many different variations on the jet engine, but the one most commonly used in passenger planes is called a turbofan because it contains a turbine and a fan. The thrust generation is accomplished by exploiting Newton's third law of motion, which states that for every action, force, there's an equal and opposite reaction, force. As air and combustion gases are forced out of an engine, they exert a corresponding force back on the engine, pushing the aircraft forward. In this way, jet engines are a type of reaction engine. The term jet engine encompasses a variety of propulsive devices, from ramjets to turbofans. Each jet engine design converts energy to propulsive power in different ways. A typical jet engine is a gas turbine, says Jeff Defoe, a postdoctoral associate in the MIT Gas Turbine Laboratory. At its simplest, it's composed of a compressor, which has blades-like wings that spin very quickly. This draws in air and squishes it, making it a high-pressure gas. Then fuel is injected into the gas and ignited. This makes the gas both high pressure and high temperature. The fan is located at the front of the engine and is the primary air intake. Large spinning blades suck in vast quantities of air, accelerating the gas and splitting it into two separate streams. Some of the air is directed around to the rear of the engine to produce thrust, while the rest is channeled into the engine's core, where it enters the next stage. The compressor squeezes the air drawn in by the fan blades, compressing it into a smaller volume and increasing the pressure. The compressor section is lined with multiple rows of blades that force the air into progressively smaller channels. Compressing the air increases the potential energy and concentrates the oxygen molecules for more efficient combustion in the next stage. The combustor introduces fuel into the compressed air and ignites the mixture, creating a high-pressure expanding gas. This is the hottest section of the engine, where energy is released from burning fuel and temperatures can climb over 2000 degrees Fahrenheit. The combustor is lined with fuel-injecting nozzles and an igniter to spark the reaction. Once ignition occurs, a steady stream of fuel ensures combustion is maintained and the expanding gas is directed downstream into the turbine section. Gas turbine engines come in many shapes and sizes. One type discussed in how turbine engines work include a normal jet engine on an airplane. The hot gas is produced by the burning fuel drives vanes in exactly the same way that wind turns a windmill. The vanes connect to a shaft that also spins the turbine's compressor. Another type of gas turbine engine, popular in tanks and helicopters, has one set of vanes for driving the compressor, as well as a separate set of vanes that drive the output shaft. In both of these types of engines, you need to get the main shaft spinning to start the engine. This starting process normally uses an electric motor to spin the main turbine shaft. The motor is bolted to the outside of the engine and uses a shaft and gears to connect to the main shaft. The electric motor spins the main shaft until there's enough air blowing through the compressor and the combustion chamber to light the engine. Fuel starts flowing and an igniter similar to a spark plug ignites the fuel. Then fuel flow is increased to spin the engine up to its operating speed. If you've ever been at the airport and watched a big jet engine start up, you know that the blades start rotating slowly. The electric starter motor does that. Then you, sometimes, hear a pop and see smoke come out of the back of the engine. Then the engine spins up and starts producing thrust. The process by which this happens is sometimes bluntly explained by the concept of suck, squeeze, bang, blow. Air is sucked into the engine from the front using the big fan visible when looking at a plane straight on. That air is then compressed in the next stage of the engine. This is the squeeze part. A second fan increases the pressure in the air by around 8 times, which also significantly increases its temperature. Fuel is mixed with the air and ignited bang, producing power. This hot, high-pressure air rushes past a set of turbine blades, causing them to spin. This turbine is connected by an axle to the compressor and this fan, so as the gases turn the turbine, this causes both the inlet fan and compressor fan to spin too. Finally, the hot exhaust gases exit the engine via a tapering exhaust nozzle, just as putting your thumb over the end of a hose pipe, reducing the exit aperture for the water. Causes water to squirt out at high speed, this tapered exhaust has the effect of speeding up the exiting gases. The hot air leaving the engine is moving at over 2100 km per hour, 1300 miles per hour, around twice the speed of the cold air entering at the front. These days, jet engines are even more advanced than basic turbine construction. Now they have huge fans in the front, and instead of shooting the gas out of the back directly, it goes through a second turbine which powers the fan up front. While older jet engines took a smaller amount of air and accelerated it a lot, newer jet engines take in more air and accelerate it a little. The result is that the engine uses much less energy. Until the 1970s, trans-Pacific flights required refueling stops. Notes Defoe. In the gas turbine laboratory, Defoe and his colleagues are working to make jet engines quieter and even more efficient by exploring design changes such as taking the engines off the wings and putting them next to the fuselage, where the air molecules have been slowed down by friction. At their largest, jet engines can have fans with a diameter of over 10 feet, but they can also be small enough to fit in the palm of your hand. It's useful to note that massive gas turbines built with the same principle as jet airplane engines are also used for power generation in natural gas power plants. There are also many other types of jet engines too, such as the turboprop. You'll know if it's a turboprop type by the large extruding propellers at the front, which is responsible for the thrust, as most of the energy from the gas is transferred to the compressor by the rear turbines. So the exerted gas is not responsible for the thrust. Turboshaft is a type found in helicopter rotors, power plants, and even the M1 tank. The process is similar to the turboprop. However, instead of driving propellers, the rotating shaft can power a variety of devices such as pumps, generators, wheels, and generally anything that spins. Modern large aircraft use a high bypass turbofan, which is similar to the standard turbojet engine, except that a large fan at the front draws in more air to the engine. However, not all of the air goes through the compressor and turbines, with most of the air actually bypassing the core and traveling through ducts on the outside of the core. On average, 5 times more air is bypassed than actually traveling through the core. These are more efficient, especially at subsonic speeds, and are also a lot quieter, while still having the ability to accelerate a vehicle heavier than a locomotive from 0 to 200 miles per hour in less than 60 seconds. A single jet engine can have hundreds of blades with the fan, compressor, and turbine sections. These blades vary in size, shape, and material composition, but they all perform critical functions in the engine's operation. Given the extreme forces and temperatures present within a gas turbine engine, metal enhancement techniques like laser peening are vital to the safety and performance of the engine and its components. Let us know your opinion in the comment section below. This is all for today. Hope you liked the video. Don't forget to subscribe to Finding Tech. Stay safe, and we'll be back soon with another video.